a lot of information, just like the first derivative does. So the first derivative gives us horizontal tangent lines, minimum and maximum, stuff like that, right? The second derivative is going to give us points of inflection and concavity from a mathematical perspective. Okay, so let's give you a basic overview. Okay, what degree polynomial is that? What? I can't hear you.
X to the fourth?
No. Third, it's a cubic x to the third. Okay? It might have humps in it. So concavity, you know what concave is, right, from science? Okay, so same concept here. We have a concave shape here, right? The cave. This is concave down. So concave down. Easy enough, right? And the other one is concave up. Wow, that was really mind-blowing. Okay. Concave up, the second derivative is positive. Concave down, the second derivative is, you guessed it. This is looking very much like a first derivative, right? Positives and negatives.
Yeah.
It's the same procedure as the first derivative. You're just not using the second derivative. So we're going to do second derivative, set equal to 0, do a sign analysis. Same procedure. Okay. This right here is the transition between the two. It's called a point of inflection.
Is it halfway point or?
It is the transition between concave up and concave down. There has to be a change. Okay, so point of inflection must have the concavity change. Okay, to be a point of inflection, you have to have that. Right? And there's your litmus test. Where is the second derivative? 0 or undefined, and then you do the sign change analysis. Okay. So again, very similar to the first derivative test that we've been working with. All right. Good. Information.
What did you say was the
What?
If you're at the end of the derivative, like, can there be like a point of inflection like the second derivative?
Say that again.
So like, you know how it's like with mean diagram or you get to do it with the second derivative? Then you have a point of inflection with the second derivative.
We don't mess with that. We just worry about the original function that you're working with usually and other points of inflection of that. Does that make sense?
What is like setting the second derivative to 0 when you're
let's see if this answers the question. we like trig so much. Oh, stop it. Someone don't puppy dog. Ooh, some issues here. Okay, so we're going to do y equals cosine x. Find the points of inflection of y equals cosine x on 0 to pi. Okay. All right, so what's the procedure? Okay. Ready, set, go. That's not right. What's the first derivative? Okay. Wow, you got that memorized. Right? Now, second derivative? All right. What do we do with that?
Equal to 0.
Set that second derivative equal to 0. And x is? It's the same as cosine.
3 pi over 2.
Pi over 2 and 3 pi over 2. All right, now what?
Now you do the sine analysis.
Yeah, so now same procedure as first derivative.
Oh, okay.
I mean, it's the same. Sine analysis with the second derivative this time. Okay. For min-max, we do it with the first derivative. For concavity or points of inflection, we use the second.
Does that mean we're plugging into the first derivative?
We will plug into the second derivative.
Oh,
The first derivative gives us min-maxes. That would be would give us incorrect information. So if you're working in the second derivative, your sine analysis is with the second derivative, right? Let's just match all that up. Okay, so f double prime at, let's say, power 4. Positive or negative? Is he right?
I believe so.
Yeah.
I hope so, because I wrote it down.
Yeah.
Cosine at power 4 is root 2 over 2. Tack a negative on it. Okay, pick a value here. Pick the easy one, please.
2 pi over 2.
Okay, 2 pi over 2, which is 1 pi. That's about all you can digest at once anyways. Cosine of pi is -1. Tack a negative on there. Okay, and then okay, that's going to be
What is that? 7 pi?
That's 7 pi.
7 power 4. See our boundaries, they gave us they gave us endpoints, so we don't want to use those if we don't have to, but we can. All right, so what does that tell us? This is concave down, concave
Oh, there's a point.
and concave down. So this is a point of inflection, correct?
Yeah.
So you have to have that change. If there's no change there, if this is minus minus, that is not a point of inflection.
So there's 2 point of inflection.
Okay, so we have actually 2.
So use the second derivative to find the concavity.
Second derivative gives us concavity and points of inflection. Okay. And in context, acceleration, right? Position, velocity, acceleration. Okay. So we'll work on that a little bit too.
So does that mean at points of inflection, it's like, what does that mean? What is the point of inflection like? Sometimes the acceleration is
It would be where the acceleration is 0, right? Because the second derivative equals 0. So if you might be asked to do intervals here, so concave down 0 to pi over 2, right? pi over 2, the 3 pi over 2. Yeah, I know, bell's about to ring, isn't it?
No, you got it.
Oh, just heard rustling. Okay, so those are your intervals for concavity. And you say a point of inflection at x equals pi over 2 and at x equals 3 pi over 2. Okay, being specific. Right?
Is it common for the equal the x values that you guys are setting it equal to 0?
Those are your only possible points of inflection. So when you get your analysis here, these are possible points of inflection.
So the sign analysis is just making sure they are.
That sign analysis just confirms that they actually are. Okay? And you have to do this in order to make sure. Okay?
Just take my chance.
Question. Don't take your chances because they won't give you credit. If you do not show a concavity change, you do not know if this is a point of inflection, and therefore you have not done the work to show it is. No work, no credit! Thank you for that. Okay. We have like 3 minutes.
Wow.
Watch the clock. There is an example in your book of a polynomial. And again, second derivative equals 0, then you sign analysis. There is an example where the second derivative does not exist. Okay, that would be that right there. If you find a spot where the second derivative does not exist, consider it a possible point of inflection and do your sign analysis around it. Okay? It's just like the first derivative. If the first derivative doesn't exist, you can still have a maximum or a minimum, right?
Yeah.
Same type of idea.
What point would you plug in the sign analysis?
You would choose points around it. So that point would be here. And you would choose a point to the left of it and to the right of it and concavity around it.
So if the second derivative is
That's what I
not,
do.
You could have, here's what you could have. You could have something like this. Right, it changes from concave down to concave up. This is your possible point of inflection where the second derivative doesn't exist. You choose a point in here.
Thank you.
Choose a point here, second derivative is positive. This assignment is not due until Friday. Of course, how many of you are going to be gone Friday?
for what?
Basketball.
Oh
my gosh.
Dang it. All right, we'll deal with that.
Well, I was gonna go back and write it on this paper, but there's a pencil over here. I did a little stutter step.
There you go.
It's not on the classroom.
Should be. Okay, tomorrow we'll do a little bit more in 4.4. And
So the problem in that is
for us, what?
the problem on that shouldn't be able to solve yet, or you can do it.
So this is it. So that's it. Friday. So tomorrow we'll add more new knowledge.
So that's all the
Wasn't really sure. Depends on weather. But I'm glad you said right on the same foot with Kyle.